Yeah, hello everyone. So today I'll talk about FANC that does incremental verification of neural networks. So this work is in collaboration with Professor Gagandeep Singh and Professor Sasha Miserovich. So recent years has seen this deep learning revolution where deep neural networks are used for many challenging tasks such as autonomous driving, speech recognition, and many more. So these deep neural networks, they are deployed through a development process as shown in this picture. So first, we collect data. Then, using the data, we train a deep neural network. Uh, After that, we iteratively modify this deep neural network until end users' accuracy and performance requirements are satisfied. These modifications include post-training steps such as fine-tuning, model repair, approximations, and all of them, many others like them. The problem with this is that this development process does not guarantee network's behavior on unseen inputs that it might face in real world. So recent research has also shown that these neural networks are prone to many of these issues with robustness, fairness, and safety. And that's why it's not enough to just check if the networks are accurate on finite set of inputs. We additionally need to check if the networks satisfy these other properties, such as if the networks are robust, if the networks are fair, if the networks are safe, and many other properties like that. So we call this new development process trustworthy development process. So in this trustworthy ML development cycle, we have additional component where we not only check the accuracy, but we also need to check behavior of these networks on certain properties. Now, what we need is we need to reason about infinite set of inputs. And for that, we need formal verification, because formal verification, we can reason about, symbolically reason about infinite set of inputs. The problem with this is formal verification, as we know, is expensive. In particular, neural network verification is known to be undecidable in some cases, but it's in general a hard problem. And what it becomes a bottleneck in this development process. So what we need, if we want efficient development process, we need to perform formal verification as efficiently as possible. Previous work has done a lot in making these verifiers scale to large networks, but all of these works have one fundamental issue, that the verifier has to run from scratch every time the network is even slightly modified. And we make a key observation that these transformations that are performed in this development process, they preserve the network behavior. So what we ask these questions, do they even have similar proofs? So if you modify the network, does it have similar proof to the original network? And additionally, say, if this is true, can we reuse the proofs of verifying original network for fast verification of its modified version? And to answer these questions in this paper, what we do is we develop a technique for incremental formal verification. So we don't design a new verifier, but our goal in this paper is to make any existing formal verifier to make it work in an incremental fashion. And so any advancement in the formal verification of individual neural network will only help us scale our incremental formal verification. So that's the goal here. So let me start with a bit of background. What's the neural network verification problem? So we have this input region IX where we are interested in verifying the property. Now we have a neural network N, which is this L-layered neural network function for which we are interested in verifying the property on. And we have this output specification psi, which is a Boolean function over the output region. So psi is a function from output region, and it is, so this green region in the picture is this part of the output region where the property is true. And what we are interested in doing is we want to know this gray region, which is the exact values that the neural network can take on this input region, if this gray region lies within the green region. So if the gray region lies within the green region, then we can say that the property holds true. If it does not, then the property, we should find a counterexample. And that's the goal of the problem, neural network verification problem. Now, there have been several works in recent years trying to build different neural network verifiers. These verifiers are categorized into two main categories, complete verifiers and sound incomplete verifiers. So complete verifiers, they halt only when they either verify the property or find a counterexample. But often complete verifiers are slow and they are not that practical. So instead, people rely on these incomplete verifiers, which are sound. See, these verifiers, they sacrifice the completeness for scalability, and that's what we focus on in this work. So our goal is to incrementally perform verification, and particularly on these incomplete verifiers. Now, let me give a bit of background on how these incomplete verifiers work. So most of these incomplete verifiers, they work based on abstract interpretation. The idea is you have this input region I. Now, on your L-layered neural network, you at each layer, this white region, it represents the exact values the layers can take. And what these neural networks do, what these verifiers do is they symbolically compute this blue region, which is the over approximation of the white region. So over approximation of the exact values that the network take. And these exact regions depend on the abstract domain used. So there are various choices for abstract domains used in the literature. So box, deep Z, deep poly, these are the abstract domains that are used for doing this sort of verification. Then these verifiers compute this over approximation layer-wise fashion, and finally they compute this over approximation at the last layer. So we, in this paper, in this presentation, we used AD as the function to represent this output at the last layer. And so the incomplete verifier takes input region I, it takes a neural network N, and it computes this over approximation ADIN. Now, what these verifiers do is they check if this ADIN region is contained within the green region, which is the property. If it is contained, then you can soundly say that the property holds. If it is not, being an incomplete verifier, it may just say that the property may not hold. So that is how these abstract interpretation-based incomplete verifiers work. And our goal is to make them work incrementally. Before going into the details of the workflow, so we consider this network modification in development process where the network is approximated. And in particular, we consider the cases when the network architecture does not change, but the network weights are modified. And this includes most practical network modifications such as fine-tuning, pruning, quantization. So what happens is the network architecture is the same, but just the weights of the network are changed. And in the paper, we identify the class of networks where our technique gains speed up. And this is sort of based on a distance metric between two networks. So we define a distance metric, and then based on that, we can decide whether our technique is useful or not. But I'll not go into those details here. And for the illustration throughout the rest of the discussion, I'll use this small neural network as example. So this network has a linear layer followed by a ReLU layer followed by a linear layer. So this linear layer, as you can see, so x1 and x2 are the inputs, and x3, x4 is the output of first linear layer. So x3 is computed as linear combination of x1 and x2. And the numbers that are on the edges connecting these neurons are the weights of the edges. So x3 is computed based on these weights of the edges connecting it from x1 and x2. So this is how the network looks like. And say we use box analysis. So box analysis is one of the abstract interpretation-based incomplete verification method. So we use box analysis on this network. And what box analysis gives us is we start with an input region, and then at each layer it computes over approximating box to the exact values that the layer can take. Now, in this particular example, we are not interested in seeing what properties we are verifying. We just want to see how the proofs are related between the original network and the approximate networks. And for that, we consider these three networks, N, NA, and NB. So NA and NB has same architecture as N. Again, just the weights are perturbed. So, and as you can see on the edges, the weights, original weights are different, and they're slightly perturbed to obtain these perturbed neural networks. So what we get here is when we do box analysis on all three of these networks, we start with the same input region. So we are trying to verify the same property. But what we see is since the weights are perturbed, these intermediate shapes that we get at each layer, they're different now because the weights are perturbed. And so what we observe here still is that even though they are different, the intermediate boxes have higher overlap. And our idea in this paper is to use this high overlap, use this observation to construct an incremental verifier where we can use the proofs of original network for its approximate versions. Now, the idea of how we do this is based on this. So can we construct a common shape that captures all the proofs? So our idea is, okay, we know that the networks are going to be modified. Why don't we construct a common shape and prove the property in such a way that now whenever we see a new network modification, this common shape will allow us to verify the property much quickly. And this has something similar to this has been done before in Spritzer et al.'s CAB22 paper, where they created this thing called as templates. Templates are defined as their connected symbolic shapes at an intermediate layer of the original network. So they compute these templates. In their work, the problem that they were solving was trying to capture multiple proofs for multiple properties on same network. So the goal was different, but the idea was to capture multiple proofs, and we use templates in our work as well. So in particular with templates, what we are interested in is valid templates on network. So we are mostly interested in valid templates, and valid templates are defined as these templates. So templates are created at some intermediate layer of the network, and valid templates are these templates. If we propagate, so for here, we have created this template T at layer K. If we propagate this template T from layer K to layer L, if the propagation at the final layer, if it is contained within the property, then we say that the template is a valid template. And we are interested in such a valid templates on a network. Note that this valid template is only valid for a particular network. And yeah. So how are these templates used? So once you have created these large valid templates, so you're interested in creating large valid templates, and once they're created, if you're trying to prove multiple properties, say you're trying to prove a property on region I1, I2, and I3, you propagate I1, I2, I3 to the kth layer where you have created your template. If this propagation at kth layer is contained within the template, then you don't need to further propagate these properties to the last layer, because then you can sufficiently say that since the template is already established to be valid and your input regions are contained within the template, so you know that even if you propagate these input regions further, they will satisfy the property. And that's the idea of using templates for verifying the properties. Now, the question here is, if you want to use templates for multiple networks, are templates created on original network N valid on its approximate version NA? And the answer is unfortunately no. Since the network weights get modified, it is possible that the region that you obtain at the final layer once the network gets modified may not lie in the property anymore. And we see that happens a lot in practice. So in this work, what we do is we create this template transformer. So template transformer is this algorithm which transforms a template T into a template T prime such that template T prime is a valid template. Now, two important things about this template transformer is it's an approximate algorithm, because creating optimal templates and transforming optimal templates is a hard problem. We show that in paper that it's a hard problem. and we have approximate algorithm that can make this transformation. Additionally, this template transformer is a cheap step in our overall algorithm. It does not take as much computation, and that's why it makes sense to, instead of rather recreating the templates from scratch, transforming these templates makes more sense. So these are the two things about the template transformer. Now, I'll go into the workflow of how our tool works. As I said earlier, this tool, it's not a new verifier, but it can work with any abstract interpretation-based incomplete verifiers. So that's the baseline verifier we use, and we build our technique on top of that. So first step is template generator. Template generator creates these templates on original network that we have. The high-level idea of template generation is similar to Swetcher et al.'s CAV22 paper, but we make several changes to make these templates such that they generalize to other networks. Those details, I'm avoiding those details in the presentation, but we make an ablation study in the evaluation that shows that these changes were necessary. The next step is template transformer. And template transformers takes this original set of templates that we created on network N and then transforms it for a particular approximate network. And this transformation basically makes sure that these templates are likely to be valid on these approximate networks. As I said earlier, optimal template generation and transformation are hard problems. And that's why we rely on these approximate algorithms that work well in practice. And our final and most important step is the verification. So in this fast verifier, we take this transform set of templates, we take the properties that we are interested in verifying and the network that we are approximate network that we are interested in verifying. And because it's an incomplete verifier, there are two possibilities that we verify the property or we just say that the property may not hold. So this fast verifier we show that it is in theory at least as precise as the baseline verifier. So there is no loss in precision in theory, and empirically we show that it gives us a speed up compared to the baseline verifier. So the fast verification algorithm, it starts with, it takes these things, it takes a neural network, approximate network NA, it takes set of templates, it takes set of input regions 5 where we are interested in verifying the property. It takes the output specification psi, and it takes a hyperparameter in our algorithm, K, denoting the intermediate layer. This hyperparameter we find out during the training time on small sample set, and it works well during the testing. Now, the first step that we have here is, since we have an approximate algorithm where the templates may not be valid, we filter out these templates that are not valid in the first step on the approximate network. Then we iterate over phi, which is the property regions where we are interested in verifying the property. For each I, which is the input region in this phi, we propagate them through the first k layers of the network using the verifier. If this ik, which is at the kth layer, is contained within any of the templates t, then we can just say that the property holds, and we can stop our verification at this point. If it does not, then we further propagate this ik from layer k to L, and then we check if this ik is contained within psi or not. And if it is, then we verify the property. If not, then we say that the property may not hold. Now, the speed up comes from the fact that we short circuit the proof whenever it is contained in the template in this step. And if you see for our running example, we have these regions I1, I2, I3 on the input, and when we propagate it to layer 2, they get contained within the template, and we don't need to verify them further. If we had propagated them to the output layer, and if you see in the right-hand side, there is this blue line. So on the right of that is the where property is true, and all these templates and all the properties even at the output layer, they satisfy the property, but we actually do not need to propagate them to the output layer. So overall, when does FANC speed up the verification? In our steps, we performed some extra steps compared to the baseline verifier, such as we created templates. So there is this cost of template creation. Then we perform template transformation. So there is this cost of template transformation. And then there was the filtering of valid templates in the fast verifier. So there is this step where you perform filtering. All these steps are the time that they take are proportional to number of templates that we create. Where do we save the time? We save the time where we don't have to propagate these properties further from layer K to L. So whenever these properties on propagation, they're captured by some template, we don't need to propagate them further, and that's where we get the saving. And we have exact time complexity analysis in the paper, but the idea is if small number of templates can capture large number of properties, then we expect speed up. Yeah, and based on that, we have our evaluation where we perform these experiments. So as a baseline, we use DeepZ verifier that uses zonotop abstraction. That's our baseline. Then we have verification properties that are considered in practice, such as patch, rotation, brightness, L0. These are robustness properties that we verify these neural networks on. And for network modifications, we consider these approximations where the networks are changed by quantization or there is weight pruning applied to the network and network gets modified. The networks that we use, so we use both MNIST and CIFAR. These are standard benchmarks in computer vision. We use those benchmarks. We use both linear layered networks and convolutional networks. And we have neural networks that have neurons ranging from 1,000 to 10,000 neurons. These are the models that we use for our experiments. Now, so this is the table that shows speed up averages across all the networks. So each row represents the properties that we are verifying, and each column represents the network modifications that are performed in that experiment. And each cell is the speed up that we get in comparison with the baseline verifier. So what we see is we even see up to 3.3x speed up compared to the baseline verifier by our approach. And another interesting pattern to see here is that when the network approximation or network modification is more, then the speed up is lower. Since the templates that we create, they generalize better on smaller modifications. So as you make your network more and more approximate, then you will get smaller and smaller speed up. And we have a distance metric between the networks that can capture this, that's described in the paper. And this is, so that's the end of my talk, and these are some important slides from the paper. I can take questions.
Thank you. Do we have questions? Okay, back.
Very nice work. Can you have shown us the speed ups? Can you tell us the exact time or at least the roundabout time it takes for these verifications?
Yeah. So it depends on the verification property, exact property. It depends a lot on the property. But roundabout, roughly, it takes about 100 seconds per property, per network. So.
Other questions? Yes.
Thank you for the talk. So these are results for the robustness properties, I assume. So do you think similar kind of results will also show up for safety properties and other properties for the networks, or do you think there will be differences over there?
There'll be some differences, but I think the idea should work. There should be some extension to make it work on those particular properties, but high-level idea should stay similar.
Other questions? Are there any from remote participants? Okay. Thanks. Let's thank the speaker again.